closing the holes in the Swiss cheese model, maximizing the reliability of operator response to alarms. My name is Todd Stauffer. I am the Director of Alarm Management here at exida. For this webinar, the audio is supplied via the GoToWebinar application. You should be able to hear and see, but you will be muted. You can respond with questions. There's a questions tool on the right side of the screen. If you enter questions into that, we'll take them at the end. If we run out of time, I'll review and address them and answer them as part of the follow-up to this presentation. So a little bit about myself. I've been involved with alarm management for more than 20 years. I'm an editor and voting member for the ISA 18.2 standard. That's the alarm management standard that is used here in the US. I've been involved with that since 2005. I helped write that standard. I'm also a co-chair for some of the follow-up activities, one of the technical reports that came after that, and currently the co-chair for the development of a new standard on safety controls, alarms, and interlocks. And exida is a company that focuses on functional safety, cybersecurity, and alarm management on a global basis. We do lots of certifications for people and devices, products. Chances are if you've worked with an SIS, a safety instrumented system, and used SIL-capable equipment, chances are that exida did that SIL assessment. We take that SIL assessment information and actually put that into our Excelentia tool, which is really a suite that allows you to address all of the stages of the functional safety lifecycle and connects to the alarm management lifecycle with a tool that we call SIL Alarm. So some background information on this presentation. It's adapted from a presentation and paper that was delivered at the 2017 Global Congress on Process Safety, which is organized by AICHE, the American Institute of Chemical Engineers. I was co-presenter with two other gentlemen. I want to acknowledge them here. That's Nick Sands of DuPont and David Strobar of Bevel Engineering. Both of those folks I work with on the ISA 18.2 committee. So if you go through this webinar and you like the material and you're interested in learning more, I would suggest going to the exida website. You can see the link at the bottom where you can download an actual copy of the white paper that goes with the presentation. So what are we going to talk about in this presentation? We will look at maximizing operator reliability, thinking about layers of protection as layers of Swiss cheese or slices of Swiss cheese. So if we look at the layers of protection here, we'll look at the analogy of each protection layer as a layer of Swiss cheese and think about how that impacts the design and operation in making the operator's job as effective as possible. So we will look at the operator's response to an alarm, trying to understand how that works, to see where it breaks down, what we can do to optimize that. We'll look at the concept of operator error to see whether that really is a thing or whether that term is used too often. We'll look at some failure modes and examples to take away some corrective actions. And then we'll shift gears to talk about the two ways to address performance. And that is, number one, through application of alarm management practices. So that'll be the first half of the discussion. The second half will focus on human factors and changing the operator's behavior to create a successful outcome. So let's start with the Swiss cheese model. That is something that was created by James Reason as a way to kind of model or visualize layers of protection. So each layer of protection is thought of as one of these slices of Swiss cheese. None of those barriers, those layers, are perfect. They all have some unreliability or some failure modes, and that's represented by the holes in the Swiss cheese. So the bigger the holes, or the more holes that you have, the less reliable is that layer of protection. But their setup or their design is that they should be able to prevent the hazard from escalating. If the hole in each layer of protection is lined up, you can see that the hazard can actually go through multiple layers of protection at the same time, leading to an accident or an incident. And if you look at most common industrial accidents, or the most famous ones that end up in the news, you'll see that rarely is there just a single failure mode. There's always multiple different layers of protection or barriers that fail, leading to the accident. Now, if we look at the slices of Swiss cheese a little bit more, the holes in the Swiss cheese then represent we'll call it the unreliability, the likelihood that it's not going to prevent the hazard from escalating. For an operator response to alarm, a nominal value that's used from CCPS is a risk reduction factor of 0.9, which means a probability of failure on demand of 0.1. So that's 10% of the time. So we could think of that as that layer of Swiss cheese, or that slice of Swiss cheese, has 10% holes in it. So what we'll be talking about is how to achieve that level of performance and how to make it better, or the things that might take away from it and actually make that performance worse. Now, one of the interesting quotes that James Reason said fits right into this presentation: "We cannot change the human condition, but we can change the conditions under which humans work." And that'll be one of the focuses of this presentation. So let's talk about what the purpose of an alarm is. In your typical process upset, normally, or before your process upset, the distributed control system is able to maintain the process variable in the normal operating range. That's the green range. However, at times you'll have a failure of a piece of equipment, or something will not work the way it's supposed to, or something different will happen, such that the process starts to go out of control, to go out of the normal operating range into the abnormal situation area. That's when we want an alarm to occur. And the purpose of that alarm is to tell the operator that their attention is needed. There is an abnormal situation now present, and they are needed to correct that situation. They must take some response. And that alarm should guide them as to what they need to do and help them to understand what has happened. If the operator takes the correct response, then the process will turn around and go back into the green zone, the normal operating range, and the alarm will actually clear. If, on the other hand, the response is not effective, then the process will continue to escalate through the abnormal situation zone into the shutdown zone. So this means the activation of the SIS, shutting down the process. Or it could be could result in a consequence, an unwanted consequence, damage to equipment or something like that. So we don't want the process to get there. So the whole purpose is the alarm would prevent that. So we want the alarm to notify the operator that their reaction or their response is needed. Now, typically you can think about alarms being used for two purposes, which is illustrated by this graph. The first is to try to keep the process within the normal operating limits. That's the green zone. The second is to try and keep the process out of the red zone, out of the shutdown or consequence area. So those are the most typical applications of alarms. Now, what we just talked about, the scenario was that an alarm occurs, the operator responds, takes the appropriate corrective action, the process turns around, is corrected, and the alarm clears. So if our alarm response or our alarm display list looks like this, where it's full of alarms and it's overflowing with new alarms, then we know that something is not working the way it should be. The alarms are not clearing, the alarms are not going away, the alarms are stale. This is a form of nuisance alarms, and this will impact the operator's performance and the ability to use the alarm system. So now let's talk about how the operator actually responds to an alarm. What steps do they go through so we can better understand how it works or how it can be improved and where it breaks down. So there's three main steps. First is the operator needs to detect the alarm. They need to see that it exists. If your human-machine interface has a lot of fancy, flashy graphics, it might be hard for the operator to detect that that new alarm exists. Similarly, if you have a lot of stale or standing alarms on that alarm summary display, it will be much harder for the operator to see that a new alarm has come in. So those, coupled with alarm floods and alarm overload, can make it very difficult for the operator to detect a new alarm. Once the alarm is detected, then the operator needs to diagnose, figure out what has happened, use their knowledge and understanding of the process to figure out what's happened and what they need to do so that they can take the right action. Now, this can break down if the operator hasn't been trained appropriately, if they have a incorrect or errant mental model of the process, and we'll talk about what that means in a second, if they're experiencing attention tunneling, focusing on a different part that's not related to the problem, or they're ignoring the alarms because they've been subjected to nuisance alarms, or they may just be incorrectly diagnosing the situation altogether. So that's the diagnose step. If that's done correctly, then we move to the respond step, where the operator actually takes action, opening a valve, turning on a pump, things like that, to correct the process abnormality. Now, how can this break down? Sometimes the operator will take no action. That's called error of omission. Sometimes they don't take the action in time, or they take it in the wrong sequence, or they take the incorrect action, which is called the error of commission. It's actually very rare that you find that the operator knows what to do and takes the wrong action. So knowing what to do and they open the wrong valve, for example. And what that also means is you'll find that most of the failures in this response model occur in the first two steps, the detection and the diagnosis step. So let's look more then at operator error and what that actually means. It typically refers to, excuse me, the last step, that response step, where you have the error of omission or commission. So what looks like an incorrect or no response from the operator. But rarely is that not preceded by errors or issues with the detect and the diagnose steps. So is it fair to just look at the operator's output and judge them based on that if we're not understanding what's going into that or what's happening before that, influencing their action? In other words, if they're subjected to nuisance alarms or they have not been trained properly on how to respond, how can we then expect a correct response? So what we may find, or what I hope you would take away, is that operator error is probably used as a reference of what has happened or an underlying cause much more often than it's really true. What we'll find is that human error, operator error, is rarely the root cause of a problem. So if you have an incident and you're doing an investigation and you come to the conclusion that it's operator error, I would recommend that you continue to look, continue to go further to try and get to that true root cause. Because if you don't get to that true root cause, then your resolution impacts may cause more damage than good. So for example, if the operator responds incorrectly because they are ignoring alarms, the action might be to discipline the operator, create new and longer procedures, or, my goodness, add some more alarms to just make the problem even worse. So that's why we really have to focus on always determining the root cause. Very rarely is it operator error. So now some background information to help us understand the human behavior, human factors in more detail. First thing we want to look at is the concept of situation awareness, which was defined by Micah Ensley. It's used very often in the aircraft industry to define human factors, and this is essentially a way to talk about understanding what is happening around you, your inputs, the visual cues, and then determining what that information means to you now and in the future. So understanding the impact and what it means, and being able to project out what it will mean in the future, so you know what actions to take now, and the actions and the impact that those actions now will have on the future. Now, as you see in the diagram, the understanding or processing of that goes through what's called a mental model. So that's really the operator's understanding of the process and how it works and what's going to happen. So we can think of the mental model as a tool that combines disparate pieces of information, allowing them to interpret what is going on and really project out what will happen in the future. So it is a key to situation awareness. Now, there are a series of areas where situation awareness can break down. They're called situation awareness demons. We've picked out a few of them that we'll focus on in this presentation. The first one is called an errant mental model. So we just talked about a mental model. What it was, it's the understanding of the process and what's happening and what it means. So an errant mental model is when you're not understanding the process correctly. And what that would do is it would cause you to incorrectly interpret alarms as to what they mean, or to discount relevant alarms that you should not discount. Another area that we'll look at is attention tunneling. This is when we focus on one area or issue to the extent that we exclude alarms from other areas that actually are important when it comes to the resolution of the problem. And then the last one that we will talk about is misplaced salience. That's when the importance of the alarm is represented incorrectly in the HMI. For example, a very important critical alarm is typically, we would expect to be represented by red and large flashing and whatever. Now, if that was used to indicate something different than an alarm, and the actual critical alarm was just a single piece of white text, that would be an example of incorrect or misplaced salience. So let's take a look at an example of where the operator response to alarm broke down. So this is a chemical plant where they were transferring reagent into a neutralization area. The reagent pumps developed a pretty significant leak that started to collect in a sump, resulted in a high-level alarm going off. The lack of reagent resulted in alarms in the neutralization area as well, and instability and more alarms there. The operator ignored the high-level alarm in the sump, and then they ignored the high-level alarm that occurred after that. They were used to ignoring the high-level alarm because that used to go off all the time. The way the sump was designed, the pump would automatically turn on as soon as the level reached the high level set point. So the operator was conditioned to know that that high level alarm basically didn't mean anything. It was a nuisance. So they also then ignored the high level, thinking that that's probably the same issue. So then when it came to trying to resolve what was going on, they were focused on the neutralization area. and looking for the source of the problem there. Of course, the source was not there, so they were not able to address the situation. Their understanding of what was happening was incorrect because they were ignoring the whole potential impact of the sump area and the leak of the reagent pump. So there was no way that they were going to be able to correct the alarm or correct the situation appropriately because they didn't understand what was happening. So it wasn't until the next shift where the new operator came in, was doing their rounds, and discovered that they had actually spilled 10,000 gallons of chemicals into the environment, where they realized what had happened. So this is an example of how nuisance alarms can impact the operator's ability to respond appropriately. So now the nuisance alarm was there because the alarm was not designed, or didn't go through the rationalization process correctly, which meant that there was a nuisance alarm going off constantly to the operator. Now, in the paper that this came from, it was an analysis of many level overflow incidents. What we found was that most of the failures actually occurred in the diagnose step. So the step where the operator needs to figure out what's going on. So we'll keep that in mind as we go forward. Next example relates to a refinery in Sarnia, Canada. In the winter, the level controller on the treated water tank froze, which resulted in a spurious high-level alarm, which the operator ignored. They then received a low-level alarm from the redundant indicator, the redundant level indicator, a few minutes later. They ignored that as well. Took no action for 8 hours until the pumps began to cavitate. Then they quickly realized that they were about to run out of water, which they did, which essentially shut down the feed of water to the boiler and shut down the whole refinery. So they lost steam to the plant in Canada in January, which is not a good thing. So when we look at what happened, what were the failures, how can we do better, we see that the operator ignored the high alarm and ignored the low alarm. And what they really should have done is use the fact that there was redundant information to cross-check one measurement against another. When that initial high alarm came in, the operator should have looked at the value of the other transmitter to determine or to validate that that was a true alarm. They would have realized that something was wrong and hopefully have proceeded down a different path then. We also found that the low-level alarm was actually just one of 15 standing or stale alarms on the alarm summary display. So it came in, it was the important one that the operator should have responded to, but unfortunately got a little bit buried on the display that had a whole bunch of already present, already active, stale nuisance alarms on it. And it also demonstrated what can happen with poor salience, because in this case the alarm summary display, in the way it differentiated the high alarm from the low alarm, it was very difficult to tell the difference. In fact, the difference only existed in 2 letters in the textual display, the difference between PV high and PV low. So some lessons that we can learn from that. Now let's apply what we just saw there, those incidents and areas of improvement, see how we can address them through application of alarm management practices. And what I mean here is the requirements and the recommendations of the alarm management standards. So I'm generally talking about the ISA 18.2 standard, which is what we use here in the US and North America. But since that standard was used as the basis of the creation of the international IEC 62682 standard, this is really a general discussion. Both of those standards define what's called an alarm management life cycle, which creates the or establishes the workflow process for an effective alarm management program. We won't go through all of the elements. We'll just hit on a few of them, including development of an alarm philosophy, alarm rationalization, creation of alarm response procedures, alarm system design, and the monitoring and assessment of system performance. In addition to those two standards, I also wanted to call your attention to that new standard that I mentioned earlier, which is in development. That's ISA 84.9103, which is functional safety of safety controls, alarms, and interlocks for the process sector. So that's essentially for equipment and alarms that are used for safety purposes but don't quite meet the requirements of being a safety instrumented system. So once that comes out, that will, I'm sure, have some new information, new requirements to apply to this methodology. Now, both of those standards define what an alarm is, or what an alarm should be. So let's look at that definition. An alarm should be an audible and/or visual means of indicating to the operator, so the target audience of the alarm system is the operator, also needs to indicate an equipment malfunction, process deviation, or other abnormal condition. So something must be wrong, something unexpected should have happened, and it requires a timely response. Other than acknowledging the alarm or silencing the horn, we're talking about opening a valve or turning on a pump. So one of the reasons often that operators are overloaded with alarms is because we use the alarm system to communicate everything that the operator needs to know, whether it's a true alarm or not. So one of the things that we need to do is separate out those non-alarm notifications, and we can use this matrix, for example, to help differentiate notifications that are abnormal or expected versus those that require operator action or are just for informational purposes. And what we need to make sure then is that only what we call alarms here are what is displayed in the alarm summary display. The other information needs to be pulled out of that and displayed to the operator via another mechanism. So now let's look at the alarm rationalization process. This is a way to review the alarms that you have to make sure that they meet the definition of an alarm that we just saw. So it's a very methodical process. First, reviewing the validity of the alarm, assessing the consequences that would occur, the cause, the corrective action, estimating how much time the operator has to respond, then assigning the alarm priority, its classification, reviewing the alarm limit or set point or assigning it, setting attributes like on delay, off delay, and deadband to prevent nuisance alarms. And then the last step is to determine whether there's any states of the process or of the equipment where the alarm needs to be suppressed or have a different limit and priority. And our SoAlarm tool can guide you through all of these steps, helping you to document the relevant information and make the appropriate decisions. We'll focus on just a couple of elements of rationalization. First, we'll look at the alarm objective analysis, where we're documenting and thinking about the likely causes, the consequences, defining that. And of course, we, for alarm rationalization, want the direct consequence of what would happen, not the ultimate consequence. So we want the direct consequence that the operator's action can prevent. We want to define the corrective action, and then also the confirmation. More on that in a second. And of course, if we can't define what the consequence is, or the only consequence is another alarm occurring, and we can't define the corrective action, then that point should likely not be an alarm. Now, I mentioned confirmation. If any of you have done rationalization before, you're probably familiar with documenting the cause, consequence, and corrective action. But what I'd like you to think about for the future is documenting the confirmation. What does this mean? This is what other process measurements in the system could the operator look at to confirm or cross-check that alarm, to validate that it's a real alarm or to rule that it's a false alarm. So what can they check to see that the alarm is really a real thing and they need to respond to it? And in fact, confirmation is something that is important to think about when you're designing the HMI as well. Ideally, you want your process graphics to be set up and showing information in a way that the operator can easily verify whether the alarm is real or not. And the idea of providing confirmation, one of the benefits that does is that's a way for the operator to unlearn their behavior of ignoring nuisance alarms. So once they've got accustomed to ignoring alarms, now you can provide them with a way to check whether that's a nuisance alarm that can be ignored, hopefully not, or whether it's a real alarm. And that will help to change the operator's behavior. Next step is prioritization. We want to assign the relative importance of the alarm so that the operator knows which one to respond to first, which one is the alarm that's part of that slice of Swiss cheese, which alarm represents the slice of Swiss cheese, so they know that that's the first one to respond to. So how do you prioritize alarms? Typically it's done based on evaluating the severity of the consequences in different predefined areas like financial, personnel safety, environmental, economic loss, etc. And then coupling that with the amount of time available, how much time does the operator have to respond, and that will dictate what the priority is. Ideally, we're shooting for just a small fraction of all the alarms to be the highest priority, such that when they occur, it's an infrequent event and the operator knows that something really significant is happening or is about to happen and they need to respond with their utmost urgency. Another step in the rationalization process is to classify alarms. Classification is a way to group alarms that have common sets of requirements for things like training or testing or management of change or reporting. So alarms, common classifications would include then things like alarms that are for preventing environmental permit violations, for environmental releases, for personnel safety, alarms that are used in layer protection, and safety alarms. Now, a safety alarm is what we're going to use as the term through the rest of the presentation to essentially mean alarms that are used as one of those slices of Swiss cheese or layers of Swiss cheese. So classification is really the best and most appropriate way to identify which of your 10,000, 20,000, 30,000 alarms are those that are providing some level of risk reduction in your layers of Swiss cheese or in your as an independent protection layer. So classification is the best methodology for that. Now, we also, to help improve the operator's response and the ability to diagnose, we may want to provide alarm response procedures to help them document or understand when this alarm occurs, what do they do? Now, all that information is essentially documented during rationalization or discussed during rationalization. The cause, consequence, corrective action, confirmation, all that stuff is essentially what we would want to present to the operator in the form of an alarm response procedure. In our SIL alarm tool, we can capture that information, create individual PDF documents for each tag or alarm, or we can actually push that information into the DCS for those DCSs that have a way to present that information to the operator directly. So if you capture that information during rationalization, kind of a knowledge capture process, then you can make it available so that all the operators get the benefit of seeing and knowing what to do when that alarm occurs. Now, from a human factors point of view, something to think about is when you create those alarm response procedures, it may make sense to set them up so that you are not documenting the known no-brainer issues, such as for an alarm, a low flow alarm, it could be a failure of the transmitter or the control valve, for sure. That's going to be probably common to everyone. So that might not be beneficial to put in the alarm response procedure. There's some evidence that it would be best to only put in those things that are unique to that particular alarm, and in essence, those things that are not obvious. From an alarm system design point of view, we'll go through this quickly. We want to make sure that the process measurement is reliable all the way from the sensor to the HMI. You want to apply alarm deadbands and on-off delays to eliminate nuisance alarms. You want to design your HMI displays to make it easy for the operator to see the alarm and confirm. And you want to focus on the enunciation of the alarm. So within the HMI, we want to design it so that the alarms jump off the page, maximize the salience so that the operator sees that new alarm come in. For safety alarms, the alarms that are the slices of Swiss cheese, we want to think about whether they go through the basic process control system or whether they should be installed independently. Good example of where that makes a difference is in Deepwater Horizon, where part of the reason that folks were injured or lost their life was because there was a delay in the enunciation of the independent alarm horn because they were relying on the operator through the BPCS to make that decision. Now, you may also find that if installed and maintained correctly, that the reliability or the risk reduction that can be achieved from a sensor in the field, a field horn and light, could actually be higher than that 0.9 value that we talked about, could actually be 99% effective. So the hole in the Swiss cheese could get smaller to help make sure that the operators know when they need to evacuate an area or not go in, for example, an analyzer shed that could have a low oxygen or a release of toxic gases. Then the final part of the alarm management best practices portion is performance measurement. So first we want to establish the key performance indicators, the target values. That goes into our philosophy document. The standards recommend what values should be used as a starting point. So we're looking at the number of alarms that the operators are getting on average, for example, per 10 minutes. We're also looking at the amount of time that the operator is being flooded by alarms. That's any time they get more than 10 alarms in 10 minutes. And the contribution of nuisance alarms, whether it's the top 10 bad actors or the chattering and fleeting alarms or the stale alarms. And then last but not least, the priority distribution of the priority of the alarms that the operators are seeing. Now, when we look at performance measurement, or we measure the performance and review the results, we want to look at it from two different points of view. We want to look at it for the entire system to make sure that the overall alarm system meets our performance metrics. But then we also want to look at the performance of the individual safety alarms as well, because the system could be working fine, but we could have a problem with the individual safety alarms, the individual Swiss cheese alarms. If, for example, one of those is a nuisance alarm, or it's occurring very frequently, or it's disabled, or it's stale, then that alarm is compromised and is not going to deliver the reliability that we're looking for. So we really have to look at both the overall system and the individual alarm. And if the performance is not met, then that means the holes in the layer of Swiss cheese will grow bigger and could grow big enough that that whole layer of Swiss cheese, or that whole boundary, becomes unuseful, not able to prevent escalation at all. So now let's switch gears and talk about the human factors and how that affects operator behavior and how we might change that. So we've been talking about nuisance alarms, which are the alarms that go off and the operator may respond to them and the alarm may not clear, or even when the operator responds. So this creates a culture or a methodology or a thinking that the alarm can be ignored. If I take corrective action and the alarm doesn't clear, it never goes away, and then the next time it occurs I don't do anything and nothing happens, then the operator develops this thinking that they don't need to respond. Kind of like the boy who cried wolf scenario or syndrome. And speaking of the boy who cried wolf, we have a interesting video that I'd suggest that you check out. The link to where that video is, which is kind of creating the analogy between the boy who cried wolf and nuisance alarms. The link to that on YouTube is shown there. So now let's look at how alarms factor into signal detection theory. And we can apply that because operators are essentially the signal detectors and evaluators in this case. They are taking in the inputs and determining what is an alarm and what's not. So the operators are doing that in an environment of uncertainty where there is noise. Now in this case, I don't necessarily just mean audible noise, I also mean visual noise. Essentially anything that will disturb the operator's environment or ability to differentiate what is a true alarm from what is a false alarm. So we talked earlier about standing alarms and how if the alarm summary display is full, that will impact the operator's ability to detect a new alarm. So that's an example of what we're talking about as noise here. So essentially we have two different probability curves for determination of whether something is a true alarm or not. And essentially there's a criteria that each operator has that establishes what their threshold is for ignoring a nuisance alarm or following a nuisance alarm out and taking a true response to it. So they kind of set the threshold individually as to which alarms they will ignore and which they will respond to, which ones they think are legitimate. Based on where that criterion gets set and what those curves look like, we will end up with some nuisance alarms, and we will end up with some scenarios where we actually miss alarms. It's very difficult to design or create a system where you don't have any of that. And you can see there's actually a trade-off between that depending upon what those curves look like. So in terms of the performance shaping factors that we can gain or think about from this analogy, certainly the greater the difference between the signal of the alarm versus the underlying noise or the surrounding noise, the better. That's what's called D prime here. So an example is to make it one way that a counterexample that would make it more difficult for the operator would be if you're using colors like red to distinguish an alarm, and you're also using that within the HMI for process piping or to represent the status of a pump, then that will create some visual noise that will make it more difficult for the operator to detect that new alarm colored in red. So that's an example of what we're talking about. Now, as I mentioned, that operator criteria, where this bar is set, is actually different for each operator. And it will depend on their history. So their willingness to accept false alarms or not accept false alarms will be different depending upon their past experiences. So if they were the operator that got burnt by a nuisance alarm in the past, they might treat it differently than an operator that's been subject to so many nuisance alarms that they've just tuned it out. So difference from one operator to the next. And that also shows up in their willingness to accept a false alarm and still go with it to the end of the response, the detect, diagnose, response sequence. And a lot of times that depends on what could happen. There's a good example in the Strobar book that I'll show you at the end, the book written by one of my colleagues that talks about the radar guys on Navy vessels during the World Wars, that their purpose was to pay attention to look for incoming torpedoes. And they would get a lot of nuisance hits, if you want to call it that, nuisance indications of torpedoes. Well, do you think they ignored those nuisance alarms? They most certainly did not, because if they did, and they happened to ignore one that they shouldn't have, they would be hit by a torpedo and they would be dead. So there was an awful lot at stake. So they were willing to put up with missing some alarms to make sure that they did not miss the true event. We can also see then that there is a trade-off between getting false alarms versus the probability of missing a valid alarm. And if we want to reduce the number of false alarms by shifting the curve, or the criteria, the operator criteria, that will then increase the likelihood of missing a valid alarm. So that means it may not be possible to totally eliminate the potential for nuisance alarms. We can certainly minimize and mitigate as much as possible, but we may not be able to eliminate totally. So now let's look at how humans respond to nuisance alarms or false alarms. What have we learned? What do we know? We've learned that a 25% false alarm rate, so 1 out of 4, if 1 out of 4 alarms is a false or nuisance alarm, that is enough for the operator to stop relying on the alarm system to detect abnormal events. So if you haven't done alarm rationalization yet, you could very well be in this situation where 1 out of 4 alarms is a nuisance alarm or useless to the operator. Another thing that we noticed is that confidence in a particular alarm, let's say a new alarm, or let's say it's our safety alarm, our Swiss cheese layer alarm. The confidence in that particular alarm and whether you should respond to it is influenced by the number of active alarms in the system. So if you have a full alarm summary display with a lot of standing stale nuisance alarms, and that safety critical alarm comes in, you are going to be less likely to respond to it appropriately than if you had a much shorter list of alarms or no active alarms at all. We also have learned that the ignoring of nuisance alarms is actually normal behavior. That's not operator error. Micah Ensley, the human factors specialist, said, a person's reluctance to respond immediately to a system that is known to have many false alarms is actually quite rational. Responding takes time and attention away from other ongoing tasks perceived as important. So what does that mean? That means if the operator is ignoring nuisance alarms to focus on other more important, more pressing operational things, that's actually what we would want them to do, and that's what's expected. So that means we don't correct that situation by disciplining the operator. We're creating more alarms. We can only correct that by eliminating or mitigating the nuisance alarms, because we're fighting natural human behavior. So what is that effect then on safety and operator reliability of nuisance alarms? We talked about earlier the nominal risk reduction factor is 90% or 0.9, so 10% of the Swiss cheese slice is holes. But what if that individual alarm is a nuisance alarm? Or what if the entire system has many nuisance alarms? Then that's likely to impact the reliability of that Swiss cheese alarm. And instead of having a 10% level of holes in the layer in the Swiss cheese, it's going to be much bigger than that. It could be 50%, it could be 90%, and maybe if it's up to 90%, you say, we can't count on this at all. We're just going to assume this is a pass-through layer. So the presence of nuisance alarms will impact the operator's ability, and if we want to visualize it, we could say that that makes the holes in the Swiss cheese even larger. So if you have nuisance alarms present in your system, you should really think about not taking credit, not taking risk reduction for the operator response to alarm, because it will not be the level of reliability that you need or that you're counting on. So how do we apply or address the human factors issues that we talked about? How do we change that, change operator behavior in line with what we're looking for? When it comes to dealing with nuisance alarms, as we said, that behavior is not changeable by training or disciplining. It's we need to get rid of the nuisance alarms. And the best way to do that is through the alarm rationalization process, where you will eliminate the nuisance alarms. When the operators take part in that, and that's what should happen, they will also see and realize that those nuisance alarms are being eliminated, and will hopefully walk out of those sessions saying, we're going to have to respond the first time the alarm occurs now, because there's not going to be a second or a third alarm to let us know. So they'll see that and hopefully incorporate that into their behavior, into their response. When it comes to dealing with alarm floods, you can apply a couple of different techniques. Automatically suppress low priority alarms is one option. You could use state-based alarming to prevent enunciation of expected alarms. And then another thing is to aggregate alarm information by system or by unit, so that the operator knows at a glance whether a certain piece of equipment or a unit is operating okay. So they know that their attention doesn't need to be spent on that particular unit. So something that would aggregate up the overall status or health or alarms present in a piece of equipment, so that they can focus on the upset area and they know that they can take their attention away from these other areas. To prevent misplaced salience, we want to design the HMI so that the changes from alarms or the introduction of a new alarm is very obvious, that it really jumps off the page. And one of the reasons that you need to make that very obvious is because humans are subject to change blindness, which means we are very poor at detecting changes, so subtle changes. So we want to make it as unsubtle as possible and make it so that it's very obvious to see when a new alarm has entered the picture. To prevent attention tunneling, preventing the operators from losing their focus and focusing on just one area, we need to provide level 1 graphics, overview graphics that show the status or key process measurements for the operator's overall span of control. This will help them maintain their understanding or situation awareness at the higher level. When it comes to mental models, we want to work with the operator to develop better mental models and more mental models. And we can use the data that we gather from alarm rationalization, to create a more rich set of mental models and understanding of what the process is about and how it works. We also want to make sure that as part of the mental model, people realize that they are prone to confirmation bias. That means that people tend to explain away conflicting cues. And this is often what happens to experts that feel they have an excellent understanding and knowledge of a certain system or situation. they are the ones that most often fall prevalent to this confirmation bias. We also want to make sure that we can transfer the mental models and the information, the experience of the more senior operators to the junior or new operators, so they don't have to go through the actual incidents or upsets that the experienced operators went through to gain their knowledge. We can just transfer that without the upsets, without having to go through them. And then another technique or a new thing to think about is what's called a pre-mortem strategy. Rather than waiting until after something happens, apply that same kind of thought process beforehand. So it's a brainstorming of, when this alarm occurs, I'm supposed to close this valve. Well, if that valve doesn't close, then what? What's going to happen? What do I do next? What happens if this happens or this does not happen? So thinking about what could happen and what you would do under those circumstances is a good way to prepare the operators for if that situation occurs. We also want to kind of train them to think and respond in a different way to alarms. And what I mean is, for example, they should change their thought process about alarms. So when an alarm comes in, they should first believe it. They should believe that the alarm is real, and they should look for confirmation that it is real to prove out their mental model or their understanding of the process. They should cross-check that alarm with other process variables to make sure that it's real, because very rarely do you have a single process variable move without others in unison or in isolation. You also want to make sure that they're very careful discounting alarms without corroborating evidence, because very often our instincts can lead us awry, particularly when it comes to confirmation bias. We can rule out things that we really should not. So when we are ruling out things, you want to step back maybe and challenge whether that's really the right thing to do. Should we be ruling out this as a potential cause, or do we need to explore it? And last, beware of factors that correlate with making it an error. In the airline industry, they find that there's some common denominators related to most plane crashes, and it's things like bad weather, flight delays, pilots not having gotten a lot of sleep, long flights, etc. So there's common denominators that kind of increase the likelihood of making an error. So we want to be aware of that. So now kind of coming to the end, the wrap-up of the presentation. So in summary, we can improve the operator's performance. We can reduce the hole in the slice of Swiss cheese for the operator's response to an alarm, and it requires two different methodologies. The first is purely alarm management, following alarm management best practices from the standards, performing a thorough alarm rationalization, including classification and prioritization, measuring and monitoring alarm system performance, looking at both the overall system and the performance of individual safety alarms, designing the alarms for reliability from the sensor all the way to the HMI with an appropriate level of salience within the human-machine interface so the operator can quickly and easily detect the new alarm. And we need to minimize nuisance alarms. So that's from an alarm management point of view. Now the second approach, or the second area, is from a human factors point of view and changing the operator's behavior. How do we do that? Through some different types of training methods, sort of what we just talked about, making sure they understand the importance of improving mental models and how they're used, and confirmation bias and how they can make wrong decisions and what's likely to lead them to a wrong decision, so that they can then change the way they respond to alarms. So two main approaches, one that's based on pure alarm management best practices, the other that's related to human factors and changing operator behavior. And you really need to do both approaches, because if you're only following just pure alarm management practices, you may not change the operating culture. You may not change the operator's behavior, in which case the impact of the alarm system changes is not going to be as significant. So you really have to take that dual-prong approach. Here's the references that I mentioned that some of this information came from the Micah Ensley book, as well as a book by one of my colleagues, Dave Strobar. So on that note, I see that we're just about out of time. We'll open it up for questions. I'll just see real quickly whether there are any questions. I don't see any right now. But what we would do is if you all have questions, enter them into that question panel and we'll review them and send the answers out as part of the follow-up email indicating where the recording is and such. So I appreciate you tuning in for this webinar. I hope that you enjoyed it and got some useful information from it. If you did, I'd encourage you to take down a copy of the actual paper that went with the presentation. And please check out our other webinars, whether they're the recorded webinars for alarm management or other webinars that are coming up on other topics, cybersecurity and functional safety, for example. So at this point, I'll again say thank you for tuning in, and please join us again next time.